We are going to continue our course with a discussion of plug flow reactors. Previously, we learned about biological oxygen demand and how to model it in the Clampock River. Now, we are going to talk about plug flow reactors so we can use them to model nitrogen in the Clampock River. Let's get started. There are two main types of reactor models commonly used to describe environmental systems. The first is the completely mixed flow reactor, which consists of a tank. The tank is assumed to be well mixed, so the concentration in the tank is equivalent to the concentration at any point or at the mass flowing out. The second is the plug flow reactor, in which a volume moves as a slice that does not mix with the entire volume. The volume commonly moves through a channel, like a river or pipe. Both are idealized models with strictly defined control volumes, which is not always possible when modeling real-world scenarios. The completely mixed flow reactor varies with time, but since the control volume of a plug flow reactor moves through a channel, the plug flow reactor varies with time and space. As with any reactor model, the analysis is affected by the choice of the control volume. You can then identify flows in and out of the system boundary and complete a mass balance. The plug flow reactor we wish to model can further be identified as a batch reactor. A batch reactor has no inlet or outlet flows to the control volume, so the primary contribution to the mass balance equation is from reaction kinetics. As the control volume moves throughout the channel, the concentration of mass changes due to advection. These effects can also be modeled as multiple reactions, but if we wish to find the change in mass over a given distance, we need to include this change in the mass balance equation. The concentration profile over the distance traveled by the control volume is shown below. In this case, the combined effects of reaction kinetics and distance cause the mass of the contaminant or constituent of interest to decrease over time. As the control volume moves along the channel, there are physical reactions occurring at the system boundary. Therefore, it is important to know not only the volume of interest, but the shape of the channel in order to determine the surface area of the control volume. The surface area perpendicular to the direction of motion is where these interactions will take place, and here is shown a rectangularly shaped channel as an example. The law of conservation of mass is used to manage mass balances. Again, it is important to define the control volume. The volume is assumed to be unchanging over time and space, which is not always true of real-world systems, but will significantly simplify our assumptions. With the batch reactor model, there are no flows in or out of the system, so the mass flow rate is constant with time and space. The mass within the system boundary may change over the distance traveled by the control volume, as well as from reactions and advection. To simplify our analysis, the reactions in our plug flow system can be assumed to be first-order kinetic reactions. Mass has the components of volume and concentration of the substance. The mass accumulation rate is the volume times the change in concentration, and the mass flow rate is the volumetric flow rate times the change in concentration. The complete mass balance can be written as the change in mass is equal to the flows in minus the flows out, plus or minus the change over the distance, and the change due to reactions. In this case, reactions reduce the concentration of the compound of interest, so the sign is negative. The full mass balance equation is written here. To simplify the mass balance, we can make substitutions to eliminate or transform unknown variables into knowns. The first transformation we will make is to divide both sides by V. This eliminates V from the reaction term and moves it to the left-hand side. So again, we are going to divide by V so that we get this term here, which will cancel out. And then we're going to remove V from the reaction term so that we're left with Q divided by V times the change in concentration minus the reaction term. Our first substitution is to eliminate the variables delta X times A for V, where V is the control volume, X is the distance traveled by the control volume, A is the surface area of the control volume. This is going to get rid of the V for any term, and so now we have this substitution here. Finally, we are going to substitute mu for the volumetric flow rate divided by the control volume surface area. This represents the average velocity of the control volume. So as a final step, we are going to get it in terms of delta C and delta X. We also have our equation in terms of delta C and delta T, here shown by the differential form. And then we can further simplify this as mu dc dx minus kc, and this is in terms of a partial differential equation. We have now simplified the equation by making substitutions. However, the plug-flow reactor changes with both time and space. To be able to proceed to the integration step, we need to transform our partial differential equation, the change in concentration over the change in time, is equal to mu times the change in concentration divided by the change in distance minus the kinetic constant times the concentration, to an ordinary differential equation, which is in terms of either dc dt or dc dx. At steady state, the concentration of C is unchanging with time. We now have our differential equation for the change in concentration only in terms of distance. To complete the integration step, let's look at the boundary conditions from our example earlier. The inflow of contaminant C is unchanging with time, so the initial concentration of C is constant. The concentration of contaminant C after some distance, delta x, is C plus delta C. We can move the C terms and x terms to separate sides and integrate with the given boundary conditions. The conditions are unique to our assumptions about the system, but we do not specify any numbers, so they will provide a general, almost indefinite form of the concentration in terms of x. The final equation reads the concentration of C as a change in x is equal to the initial concentration of C times E raised to the negative k, the reaction constant, divided by mu, our average velocity, times distance. Now that we have completed the integration steps, let's take a review of all of the things that we have gone over today. First, we solve the analytical solution for the ordinary differential equation by hand. It is important to, again, define the control volume, identify the flows in and out of the system, make simplifying assumptions, and then integrate to simplify the analysis greatly. Additionally, MATLAB tools such as the dsolve function, which involves a system of equations and an initial condition in the form of the ODE equation to solve using the MATLAB built-in function, dsolve. Another tool is the symbolic toolbox, which is a bit more involved but is equally as easy to use. For a numerical solution, which might not be as accurate but is equally as easy to use, we can use Euler's method. This can either be done by hand using a step sequence or with MATLAB using a for loop. The greater your step size, the less accurate your solution will be compared to an analytical solution. There are MATLAB tools to help you do this, including the built-in function ODE45, as well as using a for loop to replicate Euler's equation. The partial differential equation, in terms of both dc dt and dx, is shown here. The steady state, or ordinary form of the differential equation with our steady state analysis assumption is dc over dx is equal to negative kc divided by mu. And finally, after our integrated steps, the equation in the steady state form of c over x is written in two forms here, which you can use depending on which variables you have in which form. Now let's practice what we've reviewed and learned here today. A stream with a volumetric flow rate, Q, of 100,000 liters per day and an average velocity, mu, of 10 kilometers per day has a point source pollutant discharge of a contaminant C that enters the stream at a rate of 500 milligrams per day. The pollutant decays at a rate of 0.07 per day using first-order reaction kinetics. Find the concentration of C 50 kilometers downstream using MATLAB. Again, you can use any of the tools we've learned here today, as well as solving the integration by hand.